Iterative BST insert. In this lecture, we are going to discuss how to write an iterative algorithm for inserting a new node into a binary search tree. In the previous lecture, we discussed how to insert into binary search tree, what is the procedure, and we also saw the recursive algorithm for that insertion into binary search tree. Why are we specifically looking into the iterative solution? Because we want to reduce space complexity. In case of recursive solution, the recursion stack took up some space, because of which space complexity went to order of n. So we want to reduce this to order of 1. We want to make it constant space. So iteration will help us, because when you are having an iterative solution, you don't use up recursive space. Recursive stack is not used. That is why you are able to decrease space complexity. So one thing, we are not going to have separate iterative solution lectures for all the algorithms. I'm just giving you a start in first two algorithms. The reason is, one, you should know that recursion can be converted to iteration. Even though I made that statement in our previous lectures, I want to show you that it's actually not much of an effort to convert recursion to iteration. This is not much of an effort. So I just want to show that to you practically. And second thing is, once you get this knack of converting anything to iteration, then even if I write a recursive algorithm, it's okay. You can easily convert whenever you want. So let us start with iterative algorithm for BST insert. What is the process you want to follow? You want to start from the root. Let us say you want to insert some value x. What will you do? You will do the same process as search. You will see whether this particular position is empty. If it is not empty, you will see whether x is larger than this value or x is smaller than this. If x is smaller, you will go to left subtree. X is larger, you will go to right subtree. You will keep on doing this till the point you reach a leaf. Whenever you reach a leaf, you know it doesn't have any children. So you have to check whether x belongs to the left or right child of this leaf. Whatever it be, you will create a new node for x and attach as the left child of this node if x is smaller, and right child of this node if x is larger. So this is what you're going to do. Let us see the iterative algorithm. Iterative BST search. BST insert. We are inserting this time, not searching. So in this, what will be the arguments? One will be the root and second is k. K is the value that is to be inserted. So what are the steps you have to do? First thing, here you are going to insert. So first you have to create a new node. Let us call it node. So this is the newly created node in which I'll create node with value k. So this I'm not separately writing this function because there is nothing in this. You just want to create a node and put value in it. That is it. Okay. So that node is what we are calling as node. What is the next thing? You want to check whether root is empty. Root is empty means this tree doesn't have any elements. Then you should add the new node as the root. So first check is if root is null. If root is null, what should you do? If root is null, you should return new node. Whatever new node you created, this is what you will return. So that means whatever you should return at the end, that will be the root. So whenever you are writing an algorithm related to trees, after whatever modifications, if you want to return the whole tree, you always return the root of the tree. So here, if root itself is null, you will just return whatever new node you created. That will be created as that will be considered as the root of the new tree. That is it. So what is the next step? We want to write a loop. And what is the purpose of that loop? That loop should identify whenever it reaches the leaf, because we know we have a rule number 1 that insertion in a BST always happens at a leaf. So you want to start from the root and go till you find the right leaf at which you can insert. So you want to write a while loop in order to find the leaf to insert. In case of recursive solution, it was easy. You could have simply recursively called on the left subtree or right subtree. It would automatically do. But in case of iteration, it is important that you keep track of the parent as well. Because whenever, let us say you kept going till you find a null. So if you find a null, that means at that point you can't come back to this node, whatever was the leaf. So you have to keep track of parent, Because whenever you see your current node is null, you have to check whatever was the parent. Then you will find the leaf. So that is the trick to find the leaf. Always keep track of parent and current node and keep going down the tree till you reach a null node. So whenever you reach a null node, you know whatever is in the position of parent node is a leaf. So this is the logic we are going to use. What will we have? We'll have a current node. Current is equal to root. This is where we are going to start from. We need to have a parent. Parent is equal to null. To start with, it is null because root doesn't have any parent. What should we do now? Next thing is we have to write a while loop. While. What should you do in this? You should go till your current node becomes null. While current. Inside that, what should you do? You should first put parent is equal to your current. So you have decided that you are going down. So what should you do first? You should make your parent as the current node. Then you should update the current node. Why are you making parent as the current first? Because once you update the current, after that you can again fetch that and make it the parent. So you have to make it the parent first and then update current. So how do you update current? You want to check whether you want to go to the left side or the right side. If k is less than current pointing value, whatever is the value of current node, if k is the value that you want to insert. If that is less than that, you want to go to the left subtree. What will you do? You will do current is equal to current pointing left. And what is the else case? Else means k is larger than whatever is current pointing value. In that case, you will do current is equal to current pointing right. So this is done. So at this point, whenever this while loop is completed, what will happen? You'll come out of this while loop when current is null. That means you went till the bottommost point of this tree. You reached some leaf. After that, you again went to the left or right. You checked whether the value of that leaf, you checked k with the value of this leaf, and if k is lesser, you'll try to go to left child. If k is larger, you'll go to right child. But both the children will be null in case of a leaf. So what will you do now? Because you know it is null, you have to check the parent. Whatever be the parent, on that parent you have to attach. So after you come out of this while loop, you know current will be holding value null because this while came out because current is null, which means parent is the node onto which you have to attach. So how will you attach? You have to first check whether you have to attach as the right child or the left child. So if k less than, you know attachment is to be done to the parent node. You just have to verify whether it should be left child or the right child. So if k less than parent pointing value, see, in case of recursion, all these will be automatically stored because in the recursive stack, you already have the previous recursive call. So from there, you can easily fetch all the data of the previous node. But because this is not recursion, this is iteration, whatever value you want, that you have to specifically keep in separate variables. This is what you have to be careful whenever you are writing iterative solution. So if k is less than the value of parent, what should you do? You should attach as left child of parent. So parent pointing left, what would it be equal to? Whatever is your new node that you created. So why am I writing node here? This node we created with whatever was the value of k here. Into the node we created new node. What is the next step? In case this is not the case, then what is the case? Then we know k is greater than whatever is the value in parent. Else, what will you do? Parent pointing right is equal to node. You will attach as the right child of parent if the value of k is larger than parent. So this is the logic you have to write. And finally, what do you have to do? You have to return root. So you will return whatever was the root. So this is the algorithm. Let us see once again what logic did we use. This is the iterative BST insert algorithm. What did we do in this? We created a new node with value k. If root is itself is null, that means there is no tree at all. You will simply return the value of this new node, meaning treat this as the root of the new tree. Otherwise, what do you want to do? You want to find leaf, not specifically leaf if there is a parent with no left child, but you have to insert as a left child, you can do that. So what is the next thing? You will have current as root, parent as null, because you want to keep track of parent in a separate variable. I already told you, you don't have the recursion stack from where you can fetch previous value. Whatever values you need, you should keep in separate variables while you are using iteration. So you will iterate till your current is null. Whenever your current is null, you know that you have reached a point where you can insert. So you will fetch that parent and then you will see whether it should be left child of the parent or right child of the parent. Whatever it be, you will insert at the correct point. So this is the iterative algorithm. What is the time complexity? In case of time complexity, you are going from the top of the tree till some point. So in worst case, you will go till the farthest leaf. So maximum is according to the height of the tree. So what is the time complexity? Height of a BST in worst case can be order of n. So time complexity is order of n. What about the space complexity? Because it is iterative, space complexity is order of 1, because this is the whole reason why we did the iterative solution. So now we got a space complexity of order of 1.